Inference for population means. In this program, we're going to learn about T procedures to make inference about the population mean or means. We're going to learn about the one sample T procedure, the match samples T, and the two sample T procedure. We are also going to learn about one-way ANOVA testing. The one sample T. In the following example, we're going to set up and run a one sample T significance test. We're also going to run and interpret the 95% confidence interval. We'll emphasize null and alternative hypothesis formation, interpretation of the test statistic and the p-value, and finally, use of the confidence interval. We would use the one sample T procedure if we were working with one sample of data and we wanted to make inference about the population mean based on the evidence we find in our sample data. For example, if we wanted to make inference about the population mean income, here we have a sample of 50 incomes, and these are in thousands of dollars. To run the test, I would first input the variable number in my one sample T input. That's variable 1. Once I do that, I want to go to my t-test results, and here they are. So my sample evidence shows that my sample of 50 incomes has an average income of $43,480 and a standard deviation of $14,550. To formulate my null and alternative hypotheses, I need to input a test value and understand what I want to test. In other words, what do I want the data to tell me, if possible? Here I'm going to say that I want to know if these incomes give me sufficient evidence to conclude that the population mean income is greater than 40,000. So my null hypothesis would be simply, is the population mean equal to 40,000? So my test value for mu, the population mean, would be 40,000. My alternative hypothesis would be, is mu greater than 40,000? Here I see that my test statistic is 1.69, which indicates that 43.48 is 1.69 standard errors of the mean above 40,000. In other words, if 40,000 were in fact the population mean mu, my sample mean that I just got at random from my sample of 50 would be 1.69 standard errors above 40,000, the true mean mu. The probability of that happening by luck is 0.0486. Since my alternative hypothesis was one-tailed, that is, mu is greater than 40,000, my one-tailed p-value of 0.0486 is statistically significant at the 5% level of significance. So I would be able to reject the null hypothesis that mu equals 40,000 in favor of the upper-tailed alternative. Mu is greater than 40,000. So I would reject the null. The population mean mu is probably greater than the test value, which again was 40,000. However, this result is not particularly strong. Interpreting the confidence interval is the last thing that I'll show for the one sample t-test. I am 95% confident that the population mean income is somewhere between $39,340 and $47,620. This interval does in fact contain 40,000, which is sort of like saying I'm 95% confident that the population mean mu could be 40,000. This seems to disagree with my one-tailed significance result. However, confidence intervals are two-tailed. This particular confidence interval is based on plus minus 2.0096 standard errors. And again, my test statistic was only 1.691. So the result is strong enough to be significant at the 5% level running a one-tailed test, but it's not strong enough to have two-tailed significance, which is why 40 is in my confidence interval. So let's look at the results of our one-sample t-test. The result is that we would reject the null hypothesis in favor of the upper-tailed alternative hypothesis, which was that mu is greater than 40. We do this because the sample mean of $43,480 is significantly greater than the test value for mu, which was $40,000. Our evidence for that would be written like this. T for 49 degrees of freedom equals 1.69. P equals 0.0486, and P is less than 0.05. However, we found also that in the 95% confidence interval for the population mean, we found the value 40,000. So while it seems that the population mean is in fact somewhat greater than 40,000, perhaps it's not all that much greater than 40,000. In our next example, we'll look at the match samples T. We're going to set up and run a significance test. We'll also learn about the test statistic and p-value and how to interpret the confidence interval. Most of all, we're going to demonstrate why we say that the match samples t-test reduces to a one-sample t. Now let's look at an example of match samples testing. We used match samples testing when two measurements are matched to the same element in our data set. Here our data are credit card holders. So we have two measures of amount charged. One is the current year amount charged, and one is the previous year's amount charged. These measures, previous amount and amount, are matched to the same credit card holder. So we could test whether or not there's been a significant difference or change or increase or decrease in the amount charged from one year to the next for our cardholders. And the way we do that is by creating a new variable, which will be the difference between the amounts. So I'm going to input variable number 3 and variable number 2. This is going to create a difference variable using the current amount for N1 minus the previous amount for N2. And those differences look like this. So now everything runs exactly the same as my one sample t-test because I've created a new one sample of data called difference. My sample size is 50. The average difference, that is the average change in the amount charged, is $8.88. The standard deviation, $34.74. Typically for match samples t-testing, we'll use a test value of 0, which is my null hypothesis. In other words, I'm assuming no change from year to year in the amount charged on average. In this case, my test statistic is 1.81, and the critical value is only 1.68. So of course our p-value will be less than 5% because the test statistic is beyond the one-tailed critical value. The p-value also reflects that. 0.0384 is less than 5%, so yes, I would reject the null of 0 change. And I'm able to do that because my sample mean difference is significantly greater than the test value. And here the test value is 0. In other words, we're assuming no change in the amount charged. The 95% confidence interval, again, gives me a little bit of a different picture. I'm 95% confident that the population mean change in amount charged from one year to the next is going to be somewhere between negative 99 cents, that is, amount charged would go down on average 99 cents, to positive $18.75. In other words, that it would go up on average $18.75. Again, we can see that our test value of 0 is in that confidence interval just barely. And that happens because our result is not strong enough to be significant running a two-tailed test, and confidence intervals, of course, are two-tailed. This confidence interval is based on the t-star of plus minus 2.0096. My test statistic was only 1.81. So clearly, if we assume 0 difference, my sample mean difference of $8.88 would come from the middle 95% of my model, which is why my confidence interval includes the test value of 0. In other words, my test stat is not beyond the t-star value, and when that happens, the test value will always be in the confidence interval. Now let's look at our results of the match samples t-test. Here we would be able to reject the null of 0 average difference in favor of a positive difference, that is, the upper-tailed alternative that the average difference is greater than 0. Our evidence for this is written this way. T for 49 degrees of freedom equals 1.81. P equals 0.0384, and P is less than the level of significance, 0.05. However, we did again see that the 95% confidence interval gave us a slightly different picture. The 95% CI went from negative 99 cents to positive $18.75. Which allowed us to conclude that the amount charged has likely increased, but there is a chance it has not increased very much, if at all. Next, we're going to look at the two sample t procedures for comparing population means. We're going to learn how to identify the correct independent variable and dependent variable to use for a two-sample t-test. Once we do that, we'll be able to look at the null and alternative hypotheses, how to interpret the test statistic and the p-value, as well as use of the confidence interval. Now let's look at an example of our two-sample t-test. Our two-sample t-test uses an independent variable that has two categories. And the two-category independent variable is going to create two groups of our dependent variable, which is quantitative. So, for example, what if I wanted to determine whether gender has an effect on amount charged? In other words, if I group the amounts into two groups, one for the men and another group for the women, and I compare the means statistically, do I find that there's a significant difference of some type? So in this case, my independent variable number is 4, because that's the number for gender. And the two categories are male and female. And I could input these in any order that I want. It doesn't change the results of the test. The dependent variable would be variable number 3, the amount charged. So what I'm doing is I'm creating two samples, N1 and N2. N1 is going to be all of the amounts for the women, and N2 all of the amounts for the men. And those results look like this. There were 30 women who spent on average $4,122.53, and 20 men who spent on average $3,726.35. Now, while it appears that there is a difference in spending when grouped by gender, when we assume no difference, in other words, we assume that the population mean spending for both men and women would be the same, the difference between them 0, we get an insignificant result. In other words, there is no significant difference between the spending averages for the men and the spending averages for the women. So we cannot reject the null of 0 difference. The 95% confidence interval is very interesting when working with difference problems. I'm 95% confident that the population mean difference, that is the population mean for men minus the population mean for women, or vice versa, is somewhere in my confidence interval. Here it's women minus men. So I can see that because the confidence interval changes signs, starts at a negative and goes to a positive, 0 must be in my confidence interval, which is consistent with my p-value results. That is, no significant difference between the means for women and men. What if we wanted to compare more than 2 population means? Our ANOVA test will allow us to compare more than 2 population means. We're going to learn in the next example how to run what we call a 3-treatment one-way ANOVA test. We are going to learn about the null and alternative hypotheses for ANOVA, how to interpret the test statistic and p-value, how to run a post hoc analysis using simultaneous confidence intervals, and finally use of the means plot and descriptive statistics to help us understand the ANOVA results. Finally, let's look at an example of our one-way ANOVA test. This is going to be a 3-treatment one-way ANOVA, which simply means that instead of comparing 2 means like we did in our 2-sample T, in our ANOVA test we're going to be able to compare and contrast 3 means. We call these 3 treatments. So what we're going to do with our independent variable is group our dependent variable not into 2 groups, but rather into 3 groups. So our independent variable here will be coded age, which is variable 8. And I'm choosing this variable because we have coded or grouped the ages of our cardholders into 3 groups, category 1, category 2, and category 3. So I input the variable number 8, but I also have to input those category labels. These are my 3 treatments. In other words, I'm going to group my dependent variable into 3 separate samples: the low age, the middle aged, and the upper aged. The dependent variable here will again be the amount charged, which is variable number 3. So let's look at our ANOVA results. Here's my independent variable, which is 3 categories. Even though they're numbers, remember they are not quantities, they are simply category labels. And the amount charged is my dependent variable. Now first let's look at the descriptive statistics down here. Category 1 had a sample mean of $3,412.57. Category 2, a little bit more. Category 3 had a sample mean that appears to be quite a bit more. The ANOVA test has as a null hypothesis that the population means are equal. In other words, the population mean spending for people in age group 1 is equal to the population mean for age group 2 is equal to the population mean of age group 3. So the ANOVA p-value gives me a pooled result. Here is a pooled measure of the difference between the sample means, that is the observed difference between x bar 1, x bar 2, and x bar 3. Now that could be a lot or a little depending upon my pooled estimate of variability within the samples, which is measured by this number. The ratio that I see here is about 10.6 to 1, which is a lot. In other words, I have about 10.6 as much variability between the means as I do within those three samples, which means that my observed difference goes a long, long way. This is the exact same concept that we use in something simple like one sample t-testing. The p-value that I get from the F distribution here is quite strong, 0.0002, which is clearly less than 5%, so I strongly reject the null that all of the population means are equal. However, I don't know if all of the population means are significantly different. A couple of them could be about the same and only one significantly different. We need a post hoc analysis, and here we're going to use the simultaneous confidence intervals to run that. I'm 95% confident that the population mean spending for group 1 is in this range, for group 2 in this range. And I can see that those confidence intervals have a considerable amount of overlap. Looking at the means plot, I can see that just descriptively, 1 and 2 sample means are not apparently that different. In fact, the confidence intervals substantiate that because of the overlap. However, the confidence interval for age group 3 does not overlap with either age group 1 or age group 2. In other words, this result and the corresponding p-value is coming from the difference between age group 3 when compared with age group 1 and age group 2. Also, we're able to see. Now let's review the results of our ANOVA test. When we assumed equality in the population means, in other words, when we assume that all three categories of age have, on average, in the population of cardholders, equal spending on the credit card, we were able to reject that null hypothesis strongly in favor of the alternative, which is simply that the means are not equal. We are able to report our results like this. F for the degrees of freedom 2, 47 equals 10.616, and P equals 0.0002. And here we could note that P is less than 0.01 significance. So this is a highly significant result, which allows us to strongly reject the null hypothesis of equal means. However, as sure as we are that the means are not all equal, the ANOVA result is a pooled result and therefore cannot tell us what mean or means are different or not significantly different. Our post hoc analysis is necessary to interpret a significant ANOVA result. And it showed that categories 1 and 2, their mean amount charged did not significantly differ. Category 3's mean amount charged, however, is significantly different than both 1 and 2, which is what produced the highly significant ANOVA result. And finally, when I report my ANOVA results, I typically include a means plot that will show the observed difference in the sample means and usually help people understand the significance results that I'm reporting. This concludes our program, Inference for Means.